All right, hey, so we're back at it. I took a little bit of a vacation because, well, these courses are just slammed on top of each other, and so the end of the last course this past weekend was the only chance I'd really have to get away as much as I could. But anyway, we're back at it. Today we're doing chapter 11, Introduction to Organic Chemistry. I posted that video, that TED Talk, which I really enjoyed, and I think it's a good way of looking at organic chemistry because it is scary to a lot of people, but I think if you simplify it and make it like a puzzle or an exercise like that, then it can be easier. So we're going to get into it, and it comes kind of fast and heavy. So let me know if you have questions. Email me. Typically, I'll have like models and stuff to be able to work with to show you. I don't have any of that, so I'm going to do the best I can with what I got. I'll probably include some videos, some YouTube videos as well. And I'm just still deciding what to do on lab. It's a lot different not having a physical lab to work in, so I'll try to decide on that. Pay attention to Cougar View. I'm going to update assignments. I think we have I'm going to have Mastering Chemistry on some of the stuff that we'll cover today, and that'll probably be due Sunday. So if there's any questions you have, if I miss stuff, which I'm bound to do because it's hard to kind of manage everything on this end. Ask questions, give me feedback. It's the best way that I can teach is if I know where you're at, what you're learning, what you're not. So, all right, let's look at, let's go to the text. Okay, so we're doing chapter 11. Introduction to Organic Chemistry. And organic chemistry is just essentially the study of carbon compounds. So everything that is made of carbon, mainly made of carbon, is thrown into this category of organic compounds. We used to think about it being just living things. All living things are made up of carbon chain molecules. So we used to think about organic as being the study of living things, but it's really encompasses more than that. It's also small chains like gases, methanes, propanes, butanes. Those are all carbon molecules that are organic compounds. So they're included in the study of organic. And I also posted, I will post a PowerPoint or a PDF. And so it just kind of touches on some of the main things that we're going to cover today. So on the PowerPoint, you'll see here, there's different ways to represent those carbon compounds. Remember that we looked at Lewis structures. So part of your review was looking over these Lewis dot structures where we put the valence electrons around the carbon, and then we put our valence electron around each hydrogen, and then we paired them up and made these covalent bonds. Okay, and that is in essence a lot of what organic chemistry is. I'm going to go back to this table down here at the bottom, and it talks about the difference between the properties of organic molecules and inorganic molecules. Excuse me. So when you're naming inorganic molecules, it's pretty simple. You just put the cation first, which is ever the positively charged atom goes first. So in the example, they have sodium and chloride. Sodium is positive, so it'd be named first, and then chlorine is the negative anion, and it's named last, and then you just add IDE to the end, so it's sodium chloride or potassium chloride or potassium bromide. Or so the naming system is pretty simple, and I didn't go into that. Now for organic, it's a little more complicated, and there's a lot of different ways that we write out molecular formulas or structures, how it's shaped. And so knowing some of those are critical to being able to do organic chemistry. Now obviously you're not going to like dive in real deep, but having some of these fundamentals is going to be key, like just to being able to say, well, hey, this is a carbon compound, this is an aromatic ring, this is and it'll give you, I mean, if you know that it's got aromatics in there, you either know it's got smell, could be carcinogenic. There's all these properties that come along with knowing the shape and structure of organics. So that's why we're getting into it. Let me go back to this. So I was saying there's different ways that we express it. All right, so we've been looking at these models where we put the H's around the carbon. This is called a structural formula. And there's also a condensed structural formula and an expanded structural formula. I'll show you that in just a second. This is a ball and stick model. Now typically I'll be sitting in class and I'll have these models, these little stick figures that I can show you, and it kind of illustrates the shape. But it's important for you to understand that these things are three-dimensional and they have flexibility. They move around, they rotate. So sometimes when you're looking at these stick figures, you can get caught up in thinking, well, this is a rigid structure, it doesn't move. And actually I can rotate this around, so it might be similar to something else and you just can't see it because it hasn't been rotated. I don't know if that makes sense, but we'll get, when I see some examples of that, I'll show you. And if I don't, remind me. So I talk a lot and I get lost on where I'm at. If I say I'm going to show you something and I don't, email me or say I didn't explain something clearly, and I'll try to post another video and go in depth. Okay, let's see, where are we? All right, so here are, on the left is a Lewis dot structure. Now this is a huge complex Lewis dot structure. I have oxygens everywhere, a lot of hydrogens, and a lot of electrons to keep track of. Okay, so this is why we look back at that Lewis structure. When I can condense this into something simpler, this is a condensed structural formula or a line angle formula. It makes it easier to look at, use, and I mean, just it's easier to name. This is the preferred way that organic chemists write out their formulas. All right, so notice that in these line formulas, I don't have the hydrogens. You'll see here that my hydrogen comes off of the top. Let me pull up my iPad and kind of go through a couple examples. And all this is in the text as well. I'll go through the rules and whatnot. So remember, we had the Lewis dot structure where we combined all of the pairs of electrons to make bonds, right? So then all of these electrons became little bonds. And now I'm at the structural formula. So I went from Lewis dot to structural just then. Now let me erase this and say that this is a carbon atom. Okay, same thing though. I've added my H's. All right, this is a condensed, or this is a, expanded structural formula. Expanded just means I have all the H's on there as well. Okay, so if I turn this into a line formula, let me go to this next page. Actually, I'll do it right below it. It would just be my carbons. Okay, so and the carbons are on the end of each line. Every turn is a carbon. So if this was one carbon, that'd be two carbons. This would be three. All right, since I only have two in this, let's call that carbon 1, carbon 2. Then this line formula is essentially just this. Okay, so in the line formula, I'm not adding all these H's onto the ends. All right, I just have my carbons, and the carbons I don't even write out. They're just, imagine there's little dots at the end of every line. Okay, so let's do 3 now. Clear all that. So C, 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 and then I'd have all these H's. Remember, a carbon always has 4 bonds. That was a good point that the guy made on the video. So these rules make it easier to write your structures. Carbon always has 4 bonds. Nitrogen always has 3. Oxygen always has 2. Hydrogen always has 1. Okay? So if you remember that, you just kind of fill in hydrogens everywhere that you don't see them. Okay? Make sure that every carbon has 4 bonds. If it doesn't have a 4th bond, then something's wrong. You're missing a hydrogen or a double bond or something like that. Okay, so there's 3 carbons. This would be called propane, and if I were going to do a line formula, it'd just be like that. Remember, the end of every line is a carbon. So there's 3 carbons there. 1, 2, 3. 1, 2, 3. Alright, that's why line formula is way easier, right? I did all these H's and C's and everything, and I did the same formula in this little squiggly. So that's line formula. The difference in how we express these compounds, right? Structural formula, I can just write out the C's. You'll see that they have the grouping with like subscripts. So that tells you that there is 2 of these CH3s attached to this one carbon. Okay, let me make sure you're still okay. Yeah, so these 3 CH3s are attached to this one carbon, and that's how you interpret these little exponents. All right, and then everything else just kind of follows out. So the naming systems now. So those of you that did do naming in part 1, you had little prefixes like di, tri, I forget what the other one was, quadra maybe, something like that. Those were prefixes that lets you know the number of substituents, and you can still use those, but in organic we use these different prefixes to tell the number of carbon atoms. Okay, so these little prefixes are just to tell you how many carbon atoms, and it's meth, eth, prop, but, pent, hex, hept, oct, non, and deca. So the way I like to think about it is the gases, right? Because all these are methane, ethane, propane, butane, pentane, hexane, heptane. So I just kind of think about it like these little light gases. And then so I have here the line formulas for all the different ones, but the prefixes you've probably seen before and you're familiar with to some extent. Definitely up to like 5. I mean, we know we've seen penta in so many different things, so people know about the 5 and up for the most part. Octagon, heptagon, hexagon. So you've seen most of those. The ones that you're going to probably need to practice are meth, eth, propane, and butane for the 4. Okay, so those are just some prefixes. It's good to know, and you'll get some practice in. It'll be easy to pick up, no problem. All right. So I've included the rules here on these PowerPoints. I'm trying to debate what point. So let me pull up my iPad here. Now this example is a good way to start. Let me clear this off and put this on my pad real quick. So C, 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 C. And then on this side I have a chlorine. And on this side I have a bromine. Okay. So now this is my molecule. All right, now I can go in and fill in all these H's. Let's do that just so that you remember that they're there. But then I'm also going to do a line formula where we can get rid of all these and don't have to keep messing with them. Okay, remember 4 bonds on every carbon. That looks good. So now doing my line formula, I just count the carbons. 1, 2, 3, 4. I have 4 carbons. So 1, 2, 3, 4. Right? 1, 2, 3, 4. Alright, so now I'm going to add a chlorine right here. And then I have a bromine on the 3rd carbon right there. So bromine. Alright, so notice I just added little lines that shows which carbon it attaches to. I'm going to put my numbers back so you see there 4. Oh, let's talk about the numbering system. So when you number a carbon chain, you want to start with the end that has the closest substituent. So for example, let me take all these off. This was my chain. I have one substituent here and one there. So I start on one of the ends, right? I can either start on that end or this end. And whichever one I can start from and get to a substituent, one of these little breaks first, that's the end that I number first. Okay, so let me erase this and say I have a 5 carbon chain. Let's do a new page. Let's say I have a 5 carbon chain. I have a substituent here and a substituent here. Okay, so I can start from this end or I can start from that end. Which one do I start from to get to a substituent first? Okay, so let's just do both ways. If I start from this end here, it'll be 1, 2. So I get to number 2 before I have a substituent. Remember, these little lines coming off, not part of the main chain, those are the substituents. Okay, so 2 coming from this end. Now coming from this end, it'd be 1, 2, 3 before I get to another substituent. So this will be the one that I choose. So that's why when we did our numbering, we said we're going to start from the chlorine end because it was closest to the end. So there's my numbering for the carbons. Now I can name it. Alright, so I want to determine how many carbons are in my main chain. We said there's 4, right? So that's the prefix but. We know it's butane because it's an alkane. Alkanes just means that it's a single chain. There's no double bonds or triple bonds anywhere in the main chain. So where are we at? Butane. Now I can name my substituents. So when you're doing the numbering, you go from the lowest number to the highest, and then when you do the naming, you want to go in alphabetical order, so B before C. Alright, so 3-bromo, and then 1-chlorobutane. Okay, so I got some more examples. This is the example that's on the PowerPoint, and it actually goes the other way. They want to draw a condensed structural formula for 3-bromo 1-chlorobutane. And we went the opposite. We got the name from the structure. So anyway, that's our structure, and you can see that it's the same structure. It's naming. Let me think if I can throw another example out. They do some cyclos. Okay, here goes one. Give the IUPAC name for the following alkanes and cycloalkanes. Okay, so I'm on the text. Let me show you where I'm at. So I'm just looking at the practice problems. So we just came through here. This is the chart I was talking about with the prefixes. It's a little bit better in mine, so you can use that to kind of memorize these butane, pentane, the prefixes, And then it has a sample problem here. Draw expanded, condensed, structural, and line angle formulas for pentane. So we can do that real quick. It's almost like we just did. So pent meaning 5. 1, 2, 3, 4, 5. Okay, so now if I want to do all my H's, I do them like that. I just fill in until I got 4 bonds on everything. H, H. Oh, waste too much time. H, 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 H. Okay, now how many carbons? I have 5. So 1, 2, 3, 4, 5. That is my line formula. And it says what else? Expanded and condensed structural formula. So I guess the condensed structural formula would just be where you put the methanes on the end. CH2. I ain't gonna have enough space there. 1, 2, 3, 4, 5. All right, and then CH3, CH2. Then there's 1, 2, 3 of those. So I'll do 3 of those. CH3. And I can also write it out if I wanted to. CH3, CH2, 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 CH3. Okay, so this little 3 subscript just tells me that there was 3 of these there in between. All these are acceptable. And like I said, the line formula is obviously going to be the easiest way to go. So you just got to remember that each one of these is a carbon, and each one of these carbons has all of these hydrogens around them. Okay? So don't lose track of how many atoms you actually have there. Alright, back to the book. So they want us to, we were naming alkanes, and I was looking at 11.7, give the IUPAC name for each of the following alkanes and cycloalkanes. So this first one is a 5 carbon chain, which we just did, 5 carbons, penta, it'd be pentane. Let's see, the B, 2 carbon chain. So I just go back to my little table, which was right here. 2 carbon chain be ethane. Okay, eth is 2. Let's see what else. C, 1, 2, 3, 4, 5, 6 carbons. That'd be hexane. Now anything that's in that connects back to itself in a circle or a square, you'll see this square right here is called a cyclo. So cyclohexane, cyclobutane, all the other same principles apply. You just put cyclo in front. So you count the atoms, 1, 2, 3, 4, 5, 6, 7, and then add a cyclo, so it's cycloheptane. All right. So the IUPAC for those are pretty easy. We talked about substituents, right? I start whichever end the substituent is closest to. Now these substituents form what are called isomers, all right? Structural isomers. Let me show you one here on my pad here. Okay, so structural isomers just mean that, so if I were writing out a say a line formula like this, and then I have a substituent on that carbon there, and then here I have a let's see, structural isomer. Oh, my battery's dying. Give me just a second. There. Okay. So when I add up the number of carbons and hydrogens and everything for these compounds, they're going to be the same. So I'll have, let's see, 3 hydrogens there, 1 there, 2 there, 2 there, 3, 3, 1, 2, 3, 4, 5, 6, 9, 10, 14, and 5, 6 carbons. C6H14, C6H14. Okay, so if I wrote out a molecular formula like this, I might not know the difference between the two. And there is definitely a difference between the two. So I have to determine a way to name these so that I can know. And that's why we give the numbers there. If I were numbering this, I would start, let me erase these. Those are hydrogens that I was counting, these little numbers there. I wasn't naming the carbons. So let's go back there, fill that in. So if I were numbering, I could start from there because this substituent is closer. 3, 4, 5. Then on this one, it wouldn't matter because if I start numbering from this way, it'd be the same if I started numbering from this way. Okay, and why that is because remember these things rotate. Okay, so let me show you this. How can I do this? Let's say I have a chlorine. This is a carbon. That ain't gonna work. Let's try this. Carbon. Carbon. I have a bromine here. Hydrogen. Let's say this is a methyl. Okay. Alright, so now if I were writing this in a, make sure y'all are seeing it. Okay, a lime formula, it'd be 1, 2, 3, and then I'd have a bromine here, I'd have a methyl there, and a bromine here. Okay, so now, if the bromine were reversed, how should I put this? So if this were on this side, like that, okay, these two are the same molecules. It doesn't matter if I put the bromine on this side or on this side because this bond right here rotates. Alright, so you got to imagine that this thing can spin. And this bromine can wrap all the way around to this side and it'll rotate the whole molecule. And so the same can be with this bromine, it can end up on that side and the whole thing will kind of twist. So it's important to remember that when you're trying to determine whether or not it's a structural isomer. So these things can rotate and this bromine can be pointing up. Just because something may be pointing in a different direction or maybe even coming from a different side doesn't mean it's not a structural isomer. So if I go back and look at the text, it says identify each pair of formulas as structural isomers of the same molecule. So this just tries to trick you by doing that same thing. These chains move, so it's got two of them coming up in the up position, and then on the next one it has one down and one straight out to the side. But these are all butanes. All right, they're all the same. They're all the same molecule. Okay. This next one has the substituents on different carbons. That changes it. That makes it a structural isomer. Okay. So back to like what I was working on here. If I changed, this was my original BR. And then I compared that with, say, this one where BR is there, CH3 is here, and BR is there. Okay, so these are structural isomers. They're not the same molecule because the substituents are at different places. Didn't matter how I numbered. This methyl would be at the 2 position, and then this methyl would be at the 1 position. Okay. So that's structural isomerism. There's some examples in the text and some practice problems. so you can go through and practice your naming. Also included, the steps are on the PowerPoint that I put on there as well. Okay, so go back. Now next we got alkenes and alkynes. Alkenes are just double bonds. Any carbons with any organic compounds that have the double bond in the main chain is an alkene, and then anything with a triple bond in it is called an alkyne. And they have a little bit different structural properties because they're more rigid. Okay, where's that picture at? So your text has a picture of these like toothpicks right here where everything's hooked on together. So you'll see that if I rotate one of the carbons, I end up, the carbons are these black ones in the middle. So if I rotate one of those carbons, I have to rotate the other one as well. So they're kind of rigid, and they move together like that, and it doesn't have that freedom of motion that we talked about just a second ago with a single chain carbon, where it can rotate all and spin all the way around. This double bond doesn't have that flexibility. And because it doesn't have that flexibility, there's a couple different rules that we have to apply when we're doing names and stuff like that. So let me go back to the PowerPoint. So instead of looking for this substituent on this, you're going to want to look for the double bond. The end that the double bond is closest to is where you start your numbering. But the other things are still the same. You alphabetical order for the naming, for the names, and then however many carbons are in the main chain, that's the prefix that you use. A lot of similarities to how we named alkanes. Okay. One major difference is that there will be cis and trans isomers. So when there's a double bond in there, and you need to indicate whether or not the chain continues in a cis fashion, which is on the same side, or a trans fashion, which will be opposite sides. Okay, so let me go back to the text. Okay, and so I like the chlorine here on the bottom of page 379. You'll see that if the main substituents are on the same side, we call them cis, and then when they're on opposite sides, we call them trans. Now you'll see over here in the bottom right that it has two chlorines attached on the same side of the double bond. Well, you don't have to classify that one as cis or trans, okay, because the chain is the same regardless of which side you follow, if that makes any sense. You'll see as you start naming these things that if the substituents are on the same side of the double bond, it won't matter. You won't be able to call it cis or trans because it'll work both ways. Okay, and there's some little notes here like health and environment, context. I like to have the context. It helps remembering things easier. So these double bonds create these rigid structures, and that's actually very important when it gets down to things like hormones and pheromones in insects, and in medicine especially, like the conjugated bonds, which we'll talk about here in a minute with aromatics. But these double bonds allow a lot of chemistry to happen. It kind of sets up, I remember I talked about it being a puzzle that you can figure out. Well, part of building, solving these puzzles is, let's take COVID for example. So COVID might bind to a receptor in the lungs. Well, it has a very specific shape, all right, when it goes looking for these receptor sites. And that shape is based on some of these ridges, some of these double bonds and oxygens and different compounds that hang right there on the end of the virus, and it looks for something to attach to. And those structures, if we can find out what the structure is and what it likes to attach to, maybe we can create a drug that will attach to those spots instead. And so that way, organic chemistry is being used in all type of applications, and is the forefront of a lot of medicine today. So it's very cool stuff, and it's a lot to get into. Organic chemistry is most of what medicine is, getting into pharmacy and stuff. So very important. And I read those little tidbits if you want, kind of add some context. All right. So now I'm gonna go back to the PowerPoint. All right, so now we have the double bonds. We can actually have reactions across these double bonds where I can get rid of them. So it's important to go ahead and mention that. So you do need to look over the naming of alkenes, but like I said, it's pretty much the same rules with the exception of adding in cis or trans when necessary, and then starting the number from the closest double bond to the end, not the closest substituent, okay? Alkynes is the same way. So for reactions of double bonds, and this can also happen on triple bonds, you can see hydrogenation, which is the addition of H2 over the double bond. So I break this H2 in half, and then I add one H on this side, and I add one H on that side. And then hydration, so you can think about hydration just like I hydrate myself with water. That's the adding of water across the double bond, and you'll see that it adds a OH on one end of the double bond and an H on the other end of the double bond. So I want to show y'all this on my iPad though. So it's important to remember that, so we said that hydrogenation, let me do this, C2H4 hydrogenation, that's H2, right, yields C2H6. Okay, and if I was looking at this, it'd be double bond into a single bond. All right, now the other one was acid. Now it's going to say I add, I think our example was H2SO4, but it's important to remember the H2SO4 is an acid, and acids are actually hydrogen protons. Okay, so all of this across that, and let me do same one, C2H4, which is also just a double bond, so I'll write that right there. Turns into C2 H2OH, I think. So it'll look like this, and then OH right here. 3 hydrogens, let me see, wait. 3 hydrogens, 4 hydrogens, 5 hydrogens there. Okay, so the same number of hydrogens, right? I added, oh, this is water. H2O to this one here, and so it gives me this little OH, and then I added just hydrogen on this one, so it gave me C2H6. So the important point to note is that H2 is not H+. Okay, H+ is a hydrogen proton, and it is, so H2 is got protons and electrons, right? So both of these have 1 electron, and this bond has 2 in it. So remember that hydrogen molecule is for hydrogenation, and the hydrogen proton or acid is for hydration. All right, so those are the differences in those two. They both break down double bonds and make single bonds. They add something on each side. The difference is an OH is added in hydration. All right. So this was the hydration. And like I said, you'll see that H2SO4. It's important to remember that that is an acid, sulfuric acid. It's not the same kind of H2 that you're seeing here on hydrogenation. All right. And usually I'll probably use hydrochloric acid or something like that, HCl, so that that H stands out real clearly as being by itself. Or maybe even the hydrogen proton symbol, which I think your book might use. Let me go see if that, yeah, see this hydrogen, hold on. Shift, okay, right here up top, it has the hydrogen proton symbol. So if you see that, that means acid, and we're probably doing hydration. Okay. All right, and then the last thing I want to mention today is aromatic compounds. All right, so aromatic compounds are, they contain conjugated double bonds. Now, what is a conjugated double bond? That is, get my iPad, no, let's get this up. Okay. So you see how these double bonds are all separated by a single bond, but they're essentially connected. So those are what we call conjugated double bonds. Oh, I didn't mean to do that. Hold on. All right. And what a conjugated double bond is, let me write one in. Okay. So remember, all these bonds are electrons, right? So every line is essentially 2 electrons. So right here I actually have 4 electrons tied up in this little bond. And this one has 2 electrons. Now, one of the main focuses of chemistry is this sense of balance, right? We want lower energy is the way we put it. So we like to balance things out. Energies, we don't like to have if there's a bunch of positive charge over here and a negative charge over here, they'll start to attract to each other, and it's trying to create an equilibrium or a balance. So what happens in these conjugated double bonds is that I start to share these electrons within the ring. Okay? So for example, this little bond here, this electron jumps to this bond here. And then this electron will jump to that bond, and so on. And they'll just keep doing this little cycle. And so what ends up happening is my bond, instead of just having the double bond in 3 sections, it's essentially got the bond going all the way around the ring. These things are moving so fast and they're jumping so fast that by the time this electron gets to this bond, this one's already gotten to this bond, and so on and so forth. So they're moving so fast that we just represent it as a circle. And essentially the double bond character, or the characteristics of a double bond, can be seen anywhere throughout the whole ring. So this ring is called a benzene. And when you name stuff and you see this ring in there, you can probably just say benzene. Although there are commonly used aromatic compounds that you'll just have to know the name of and be able to recognize when you see them. So that list of those is here, and I don't know how many is going to be on Mastering Chemistry, but I know that the main ones that we usually look at are these first 4: toluene, phenol, aniline, and benzoic acid. Okay, maybe styrene down here on the bottom right. But we'll go through each one as they come up. So this one has its own naming system, and it's fairly similar. So you just want to name, it's fairly similar to the alkane rules, where we said you name where the numbers are the lowest. So back to my little pad. remember that on the alkane, if I had this, let's say, let me add a couple more. Let's say I got one there, and then I got one more here. Okay, so now which way would I go to name? I can go this way or this way. Or let's do number first. Okay, so if I start here, 1, 2, 3, 4, I have a substituent on the 2 and I have a substituent on the 3. So this way would be 2, 3. If I start from this way, I'd have a substituent on the 1, 2, 3. That's so 3. Then I'm back 4, 5, 6, 7. And then I'd have one on the 5 and the 6. So this way would be 2, 5, 6. And this way would be 2, 3, 6. So this group is the lowest numbers. That'd be the way that I would number. Same thing on aromatic compounds. Excuse me. If I have aromatic ring, benzene in other words, and let's say it has a methyl there, methyl there, methyl there. Where do I start my numbering? So if I were to start right here, I would have one on the 1, but then my next one would not come to the 3, 4. Okay, 1, 3, 4. So that might be okay. Let's check something else out. Let me start here. 1, and if I go to the right, it'll be 2, 3, 4. So my number will be 1, 2, 4. Let's go another way. Let's just do them all here. There, close that. Okay, so now let me go this way. 1, 2, 3, 4, 5, 6. So that way would be 1, 4, 6. What I didn't mean to do that. 1, 4, 6. This is the one that we're going to use. So that was the one that said we went 1, 2, 3, 4. Okay. So that'd be whichever way the substituents arrive earlier, that's the way that you number them. And then alphabetical on the names. It's important to recognize when there is a commonly used name there. So like this first one has that toluene, which is the CH3 coming out the top. So they just start with toluene and then name it from there. So 4-chloro, 2-nitro, toluene. All right. And it's automatically assumed that the main group, the CH3 and toluene, the OH and phenol, this red group right here, that's located at the 1 position. Okay, so that gives you some orientation. When I say 3-bromo, 4-chloroaniline, the aniline is the one, the N is the 1 position. Let me do an example. What did I just say? 3-chloro. I'm just gonna write something I don't even know what it is. 3-chloro, 2-bromo, aniline. Okay, so now I'll start with my aniline first, which is that NH3, NH2. Okay, so that'd be my 1 position. It says 2-bromo, and it doesn't really matter which side because I'm going to put the chlorine on the same side, right? So 2-bromo, 3-chloro. Okay? So always start with whatever the main substituent is as your 1 position, and then you can count out from there. So that is pretty much it for that. Let me see if we got anything else on the nope. Okay, so just a lot of naming and some little rules that you'll have to go through. I got some mastering chemistry I'm going to put up. Y'all take care of that. I'm also might add some other videos from YouTube, just people that have been doing this more and have good computer skills that can illustrate things better than I can. So I'll add those videos as well. If I didn't do a good job of explaining it, go on there and take a look at some of the other videos and see if it helps to make some things click. Yep, that's it for now. Be sure to look for a lab that we'll be doing later on today. See y'all.